I'm Eric Owenell. I'm the author of The Elements of Parallel Computing, published by CRC Press. I've been a researcher in computational science for the past few decades, and I've been teaching parallel programming at the undergraduate and graduate levels for the past 15 years. Over those years, I've used some good textbooks, but they've quickly gone out of date because they focused on particular hardware architectures or programming models. What I've done with my book is focus on the principles. After all, there's only a limited number of principles that keep reoccurring in parallel computing. For instance, single instruction multiple data, or SIMD, execution is an early idea in parallel computing, and it's reoccurred recently as the execution model for graphics processing units. There are 8 chapters, starting with an introduction, followed by 4 chapters with the core elements of parallel computing. And then there are 3 chapters with some detailed case studies. All the examples in the book are illustrated using both pseudocode and using diagrams, as well as discussion in the text. I've been inspired by the work of design patterns applied to parallel computing. In this figure from chapter 1 of my book, I show on the left Berkeley's R pattern language hierarchy, and on the right the corresponding chapters of my book. I don't take a formal design patterns approach, but I do discuss the common algorithmic and implementation patterns that are relevant to parallel programmers. Let's look at one particular example, that is the prefix sum. It's an example that illustrates how I use pseudocode instead of a particular programming language to illustrate my algorithms and implementations. Here are 2 illustrations of the Hillis and Steele SIMD prefix sum algorithm. In the upper figure, you can see the operations taking place on the array, and in the lower figure, you can see the task graph. Here's the Hillis and Steele algorithm expressed using the set notation that I use to represent data parallel operations. In the last 3 chapters, I present 3 case studies: the single source shortest path, the Eikonwell equation, which is basically a continuous shortest path problem, and finally the planar convex hull. In each case, after presenting the problem, I describe the common sequential algorithms. Then there's a parallel design exploration where I explore the possibilities for decomposition. Then select algorithms from the literature are discussed in detail. Here's an example illustrating a SIMD Bellman-Ford algorithm, where we start with 3 vertices, 3, 5, and 6 in the queue, extract their neighbors, perform the relaxations using an atomic min operation, use a compare and swap to avoid duplicates, and finally produce vertices in the queue, vertices 5 and 7, for the next round. Notice also that a scan is used, which is the general term for a prefix sum. I'll be making implementation of many of the algorithms in the book available on GitHub in language models such as OpenMP, Silk+, MPI, and CUDA, and I also welcome your contributions. I look forward to hearing from you as you use this book in your parallel programming course.